We've seen in Chapter 3 circuit simulation of the Getting Started material that some PDK components come with simulation models that you can use out of the box to run simulations. However, with IPKISS you can define your own models to match custom components or extend the utility of a PDK model for your application. The most accurate method of characterizing a component is to perform physical simulation of the device by solving the Maxwell equations with the appropriate boundary conditions. There are many techniques to achieve this. These methods are a necessary step to fully characterize and verify a device's behavior. However, they are computationally intensive, especially for larger and more complicated devices, which can lead to very long simulation times. The good news is these types of simulations don't need to be repeated over and over. Once we have the data, we can extract the parameters to build compact models. A compact model characterizes the behavior of a component by representing it as an S-matrix, which describes the relationship between the input and output optical signals of a device in terms of reflection and transmission coefficients, and optionally a set of differential equations. This allows for fast and accurate simulation of large circuits in frequency and time domain. To build a component model, we use the compact model, which is accurate enough to have predictive value and create a circuit simulation in Caffe in frequency and time domain to see the response between any two ports. Let's look at how to make a compact model. There are 4 steps. We start by creating a class, which inherits from i3.compactModel. Next, we define the model parameters, and a parameter can be anything that influences or defines the behavior of the component. Here we have the center wavelength and the reflection and transmission coefficients. We then specify the inputs and outputs, which we refer to as terms or terminals of the component. And then we write down the S-matrix based on the terms and parameters. The polynomial coefficients of the reflection and transmission are evaluated at the wavelength of interest, and the result is placed in the S-matrix. We will now attach the model to the P-cell by using Circuit Model View. First, the model is instantiated by filling in parameter values, and then is simulated over a wavelength range from 1.5 to 1.6 microns. Do not worry about where the values for transmission and reflection come in, this will be covered later. We then plot the S-matrix. The transmission and reflection values are converted to a decibel scale for easy comparison using the IPKISS function i3.signalPowerDB. We now go to the PyCharm environment and open up compactmodels.py in the Component Models chapter, and we can see all of the steps to build the frequency domain simulation we've just discussed. We have our class, parameters, terms, and calculate S-matrix. We then move on to testing this model by using transmission and reflection coefficient data and adding them to our circuit model. And we then plot the results. So if we run this script, here we see the transmission and reflection. Following the same approach, it's easy to run the model from simulation or experimental data. As an example, we will use simulated transmission and reflection values for our MMI obtained with a third-party solver. The data is then imported in Python, fitted using NumPy, and passed to the compact model. The next step is to import our dataset before fitting with a polynomial to allow us to interpolate for any wavelength. We utilize the NumPy module's polyfit function to implement a polynomial fit for our data. This approach minimizes memory usage and enhances simulation speed. By passing our wavelength coordinates and corresponding transmission and reflection values, we obtain a stable fit. Normalizing the data ensures each coefficient contributes equally, improving the robustness of the fit. Here we've opted for a polynomial degree of 7, striking a balance between model size and accuracy. There are many other fitting methods available in Python, so other methods can be used depending on the device that you are trying to model. We then pass these transmission and reflection coefficients to the test circuit model. So we return to the PyCharm environment and open up data-driven models.py, where we see all of this configured. We see the imported data for transmission and reflection, the coefficients we've selected and the polyfit of 7, and the plotting. So we run this, and we will compare the model to the data. We see a good fit for the transmission data, but it would be a good idea to increase the fitting order for reflection to reduce the difference between the data and the model. Every design in IPKISS has a P-cell, and it is the most basic class in IPKISS. It is used to describe the behavior of an optical or electrical component, such as its physical geometries, the connectivity, as well as the compact models used to describe the behavior to a circuit simulator. At this point, we can assemble everything we've done together and attach the model to the MMI P-cell. This is done through the circuit model class, which acts as a container for a compact model. Similar to how the layout view describes the shape and layers of a component, the circuit model view contains information about how the component will behave in a circuit simulation. We begin a simulation by instantiating the circuit model and calling getSMatrix. Calling getSMatrix will run the frequency domain simulation of the circuit modeling cafe, returning an S-matrix. So in the PyCharm environment, we go to the component simulation.py file, and here we will implement our P-cell. Instead of importing the whole data set and fitting it each time we want to instantiate a component, we perform the fitting once, then save results to a JSON file. This means we only need to load the coefficients for each parameter, which improves the speed of the simulations. And here we see a small function that will open our JSON file and return the data. We will not add a layout to this class to keep the script simple. However, you would add this here if you were making a complete component class. Instead, for this example, we will just add the circuit model class and add some properties that are required for our compact model. The generate model method is where we call our MMI model and pass in the parameters for the component. We import the model parameters we want to use from the JSON data file, instantiate our model and call the circuit model class. We pass the parameters for this MMI into the circuit model, and now we have a component with a complete model that returns an S-matrix we can use in circuit simulations. We can call the getS-matrix method for our component in the same way as we did for circuits and plot the response. So now we run the script. And here we see the simulation results for the transmission and reflection. Now it's over to you. In the Component Models chapter, in the Exercises folder, you can find exercises.py. Try to finish the compact model for the basic waveguide, and if you get stuck, we do have a solutions file for you. So let's have a quick look at the exercises.py file. Here we can see an incomplete script. Try to fill in where you see the ellipses. If you get stuck, we do have a solutions file. So let's look at a more advanced example. Our circuit simulator cafe is equipped to conduct time domain simulations as well. Earlier we looked at frequency domain simulations, which are useful for analyzing the steady-state behavior of photonic integrated circuits, particularly for linear and time-invariant components such as filters, couplers, and resonators. Time domain simulations, on the other hand, are crucial for capturing transient effects and dynamic behaviors due to the propagation of light pulses, switching of optical signals, or modulation. Time domain simulations are well suited for capturing these transient phenomena accurately. Although the specifics aren't covered in this introductory training, this example serves as an initial introduction. The initial steps should feel similar since the overall format of the compact model remains consistent. So we create a new class for our new compact model, Heater Broadband Phase Error Compact Model, which inherits from i3.compact model. We define a new list of parameters. We define our optical and electrical terms. And finally, we calculate the signals. We now have two additional methods available to us: calculate signals and calculate dy/dt. For calculate signals, it captures the time dependence of the output signal on the input signal. In this case, we take the length and group velocity of the waveguide into account to calculate a time delay. Calculate dy dt includes differential equations that describe the state of the system, for example the temperature, but we won't use this in this example. We will implement the time dependence using the following method, where the output at each port is determined by the delayed and scaled input signal from the other port accounting for transmission. To run a simulation, we also need to specify some sources. We're going to send a constant optical signal through the waveguide while linearly increasing the applied voltage. We start by creating a time step variable for our simulation dt, and then we create our driving voltage function, which is a ramp function. We will create a constant unitary optical source and the driving voltage using the ramp function. Then we use i3.connect components to connect our component to the optical and electrical sources and an optical probe. Now we can make a test bench circuit that connects the sources to the waveguide, comparable to what you would do in a lab. The simulation is started by instantiating the circuit model of the test bench circuit and running getTimeResponse. So now we run the simulation and calculate the time domain response of the circuit model over a specified time range and with a specified center wavelength. The result is stored in the variable result. In the Advanced Examples folder, we find a fully scripted version of everything we've discussed in this tutorial. All of the steps to build the time domain simulation, a class, parameters, elements, calculating an S matrix, is all contained here. You can play with this script by varying the parameters that you see, and then simply running the script. And what we get at the end is a time domain simulation with changing phase with increasing voltage. In this tutorial, we have looked at how to build component models by building compact models as a fast and predictive way to understand how a component will behave. We add the relevant parameters and terms to the compact model and then calculate the S matrix. We then use imported data to fit a polynomial and store the coefficients in a file to be used when running simulations. Lastly, we set up a test bench to be able to run time domain models and looked at an advanced example using a heated waveguide. If you'd like to learn more, please visit our Lucida Academy for many more interesting examples. If you have any questions, please contact us at support@lucidaphotonics.com.